So in the last part, we talked about the phase diagram of pure substances. So we'll now discuss briefly, I'll give you an overview of the properties of properties of mixtures, basically the thermodynamic of mixtures. Now, when you talk about mixture, if you remember your old literature, that if I have, say, a mixture of two components like A and B, which are non-reactive, so and then suppose we are mixing these two together, so the first thing we ask this question, suppose A and B are both liquid. Let's take an example. Let's say A is water and B is, say, ethanol. And then if we want to actually plot how much the volume will change if I add a little bit amount of B into A or in the reverse way. So what I'm plotting right now is basically the mole fraction of ethanol, and I'm adding ethanol into water. Now, interestingly, what will be the partial or the molar volume of water? So we know that the molar volume of water, if the mole fraction, it's a fraction, so it can go to 0 to 1 only. Now, when it is 0, so it's pure water. So the molar volume will be nothing but 18. So because we know that so the water, if I take the density as 1 gram per cc, and if we take the fact that molecular weight of water is 18 gram per mole, so that will give you the molar volume. And then we see that for ethanol it will be like 58. You can easily calculate it from but the density is required. And then the variation of the partial molar volume will be something like this. So this curve is for partial molar volume of water, and this curve is partial molar volume for ethanol. Now the partial molar volume is defined as the change in the total volume if we just add some amount of the ith component, and this is the definition of the partial molar volume, the change in the total volume. Now since water and methanol are miscible, now we see that the volumes just do not get added up. So it's a very the nature of the curve is very complicated. As you can see, there is an initial increase in the partial molar volume, and then there is a decrease, and similarly there is a decrease in the partial molar volume of ethanol, and then it increases. So in the pure case, like when mole fraction of ethanol is 0, it will be of course 18 because it means actually pure water, and similarly if the mole fraction is 1, it will be pure ethanol, so it will be 58. But in between we see that the volume is not actually being added up, as the two one constituent is constantly being added into the system. Now similarly, just like partial molar volume, we can also define something relevant to the chemist, actually the chemical problems. And as we said that most of the chemical reactions are done under constant pressure and temperature. The question we are asking is that at constant pressure and temperature, if we also change the number of moles of the constituents, which quantity we should look at, and that is by the choice is obviously the Gibbs free energy. So in a similar way, we can actually define partial molar Gibbs free energy, so which is defined as in the same way like we define the partial molar volume. So this is the change in the Gibbs free energy if we keep on adding one constituent and keeping all other parameters same. So in this case, actually I have to keep pressure and temperature fixed, and also the other constituents I have to keep fixed. So and then I have to take the sum over I. So here actually I have to always keep in mind that when I am changing one component, I am keeping the all other constituents same. For example, if I have I equal to A and B, So I have only two component system. So the partial molar volume will be defined as the change in the volume if I change the amount of A times the change in amount of A, but when I did this change I kept uh, the amount of B constant and also other thermodynamic parameters which are pressure and temperature constant, plus I had del V del NB at constant pressure, temperature NA into dNB. So this is the overall expression. So similarly, if we want to write an overall expression for dG or the partial change in the Gibbs free energy, so then for a two component system it will be something like del G del Ni. If I have the components as A and B, I'll have constant pressure, temperature and NB into dNA, plus I will have the corresponding change with respect to B if I keep the pressure, temperature and amount of A constant. So in this way you can actually define the partial molar volume, and one of the interesting thing is that since we are talking about the change in Gibbs free energy per change in the mole, so we know that the Gibbs free energy per unit mole is nothing but the chemical potential. So by definition we see that the chemical potential of the ith component is actually defined as del G del Ni at constant pressure, temperature and all other components. So we can actually rewrite this equation, the dG equation, as it will be actually sum over mu I dNi, sum over I. So the mu I is defined as this quantity. So we know that actually the total differential of dG is nothing but VdP minus SdT. This is for one component system, this part, where actually I have only a pure substance. But for a mixture I will have an addition, because for mixture I can also change the number of moles keeping the pressure and temperature constant, and that gives rise to an additional term. So this is basically the change in Gibbs free energy, a differential change in Gibbs free energy for a mixture. Now we can actually just like we define the mu I as a derivative in G, you can also express it in terms of derivative of the other thermodynamic parameters, let us say for example the internal energy. Now how do you do it? Because you can always get back your expression for U, because you know that G is nothing but H minus Ts. Now what is H? H is nothing but U plus PV minus Ts, and then you can actually take the derivative, what is the relationship between dG and du, and from that you can easily figure out that if we use that, so then you will see that this mu I is also equal to the partial derivative of the internal energy with respect to the change in constituents when the entropy and the volume and the all other constituents are kept constant. Now these are actually equivalent definition. I can define the mu I in terms of the change in Gibbs free energy, I can define the mu I in terms of change in internal energy, but for Gibbs free energy change, the other than the constituents, the constant parameters are pressure and temperature, whereas for internal energy the constant parameters are entropy and volume. Now since in most of the chemical process I mean stated it again and again, we have the natural choice that the pressure and the temperature are kept constant. This is a more useful definition to use than this definition. So although these are all equivalent definitions. Now let us move ahead, and then after this discussion we usually in the basic thermodynamic course we take the total derivative of G, because and then you can always integrate this equation and then again you can differentiate it, and then what you will figure out is that you will get a very interesting relation that sum over Ni d mu y is basically 0, or if I and this is very easy to show because I have mu I dni. When you integrate it, it will be mu I ni. Then when you take the derivative once again, you will have derivative with respect to mu and derivative with respect to n, and then you arrive at this equation. This sum is over I, and this equation, as you know, is known as Gibbs-Duhem equation. And then what usually we talk about is basically the thermodynamics of mixing. And the first thing which we talk about there, if we have say two ideal gases and if we are just mixing them, what will be the change in the Gibbs free energy? Again, this is basically the driving force here is entropic, in the sense that we have actually one particular species confined in one particular region, let's say something like that. So I have say A molecules are here, and suppose these are all gaseous species, and then I have actually B molecules here confined here into two chambers, and then all of a sudden I remove this boundary between them. So there will be spontaneous diffusion of the molecules, and the A will occupy the entire space and B will also occupy the entire space. The Gibbs free energy will of course decrease due to basically mixing, and this mixing we can formulate very easily, and what we will see is that the change in Gibbs free energy, the total change, and this change is due to mixing. So we are using a suffix as delta mix G is nothing but nRT sum over, this is the general expression. If we have actually a lot many components, it will be summation over xi ln xi, where xi is the mole fraction of constituent I, mole fraction of I. So thus we see that this is basically a general equation for the Gibbs free energy for mixing. Now moving on, we see that we talked about mixing, and then the next thing which we always emphasize is basically what is the thermodynamics of solution. Now when you talk about solution, we have basically two constituents, one is solute and one is solvent. So the question here is that suppose I have a solvent to begin with and I am slowly adding a solute into it. Now if you can actually express everything in terms of the partial pressure, let's say Pa is the or the pressure or basically the vapor pressure also, you can think about it like what I am saying here is that suppose I do this experiment in a closed vessel and I have a pure solute, and then I will have a vapor pressure which I am denoting as Pa star. So star actually denotes the pure component, and then I have something like say A plus B together, where B is the solute in this case, and the solute does not evaporate. I am saying that only the solvent evaporates, which is A, and now the A actually will be dominating because it's a solvent by definition. So what we see here is that the you can actually do the thermodynamics, and then you will find that this chemical potential of A will be nothing but chemical potential of A in the solution, where actually in presence of B it will be nothing but the chemical potential of A, the pure A, plus RT ln Pa by Pa star. Now again in this equation or in the previous equation for delta G mixing, you see that we have used nRT, and this nRT comes from PV equal to nRT or the ideal gas equation. So here also we are assuming that these vapors are actually behaving ideally. Now if we proceed with this, we can easily figure out that we have to establish a relationship of this Pa by Pa star. Now Pa by Pa star are again Pa is basically the pressure or the vapor pressure of the solution, and Pa is the vapor pressure of the pure solvent. Now what we can assume this Pa and Pa star, the relationship between them is that Pa and Pa star is nothing but related to the mole fraction of A. which is not very correct, because as you can see, if the mole fraction is 1, then Pa will be equal to Pa star, which is fine, and which has to be. But in other cases, it's an approximation, and this is basically known as Raoult's law, which is valid for ideal solution. And this Raoult's law was developed from the perspective of the solvent. Now again, the solvent and solute are all arbitrary, in the sense that we call solvent that part of the solution which is present in large excess, and solute is the smaller part. Now if we actually plug in into this original equation, then you basically see that mu A is basically mu A star plus RT ln XA. Now this is again this is an approximate equation, and this actually is followed from Raoult's law. Now if you want to actually plot how it will look like, if I just plot the mole fraction and how the partial pressures are changing for A and B, we can actually have a similar plot like we did for our partial molar volume. Now if think about it, like suppose let us plot the mole fraction of A, so which can go from 0 to 1 because it's a fraction. So when it is 0, the pressure will be totally equal to the pressure of B, and this is pure B, so it will be PB star. And when it is purely 1, the pressure will be like PA star, because it's all everything is in A, so it's a pure pure solvent. So the way I have drawn it here, that PB star is higher than PA star, but it's not necessary. And then in between you will see that the total pressure, that should actually the total partial pressure, that should change from PA star to PB star, that is for sure. So the partial pressure, like how the B will change, B actually when the mole fraction of A is 0, it will be PB star, but when it is 1, it has to be actually 0, because this axis is basically the pressure, partial pressure. So the B curve should be like this. Similarly, the A curve should be like this, and this should be the total partial pressure. So this curve is for B, this curve is for A, and this curve is for the total vapor pressure. Now what is interesting here, that in reality actually you will not see it, we will plot the real situation, and the Raoult's law as you can see is basically tells you as if it's a linear relationship of the vapor pressure with respect to the mole fraction, which is obtained here, which is shown here. So if I have actually more mole fraction, I mean if it reaches to the pure thing, of course it will be the vapor pressure of the pure state, which is the pure solvent, which we denoted as star, but in between we are assuming that it obeys a linear relationship. However, we can actually think what about the perspective with respect to the solute. Now suppose if I add a little bit of the solute and the solution is very much dilute. Now think about it, suppose you take sodium chloride into water. Now when sodium chloride is very much impure, so the salt, the sodium chloride actually sees or any solid, let's not talk about sodium chloride because it's an ionic solid, let's talk about suppose I have sugar, and then all these sugar molecules in the pure phase means actually it is a solid sugar molecule. So in that pure phase, suppose the solutes are like this in that solid. So this is nothing but pure solute, and the solute we are denoting as B. But moment I dissolve it into a solution, in an ideal solution, then what will happen, due to solvation, these solute molecules will be far away, and then all these solvent molecules, let me actually denote it with a different color, they will actually surround the solute molecules. So this will be the situation in a solution. So what we see here, the solutes actually experience a very, very different environment in a solution. So what will happen is that their mole fraction or their partial pressure will be very, very different. So this is B in solution. So if we plot the similar quantities, but this time I am plotting the mole fraction of B, and remember that B is our solute. Now when it is 0, now there is no basically solute present, then what we will see here is that it should actually, if the Raoult's law is valid, and suppose this is going to PB star for if 1 means actually the B is in pure thing, B is pure means actually now B is acting as a solvent, and then the total vapor pressure will be nothing but equivalent to PB star because it's in the pure state. But what happens in reality is that the real curve looks like something like this. Let me draw it once again. So at a very early concentration, we'll see something like this. Now look at it carefully, that at a higher mole fraction of 1, a higher mole fraction, when actually xB is approaching 1, which means now B is in excess. If the B is in excess, we can actually try to draw a figure. So it will be something like this, and then there are less solvent molecules around it because the solvents are A, and then this actually now resembles something like pure B. It is close to that. So actually now B starts behaving as if it's a solvent, and then for the solvent we said that the Raoult's law is valid, so actually there is a nice agreement. However, when there is a question of dilute solution, when B is present in very small amount, then there is a significant departure, and to account for that, Raoult basically said that okay, we can actually take the initial slope. So the drawing is not very correct here, so we can actually try to redraw once again because the slope was very higher. So let me just redraw it once again. So for solute, we are saying that the initial slope will be very different, and then we can actually take a slope which is basically fits to this initial amount, and this again at a later part actually it matches because actually it's just like Raoult's law. This is basically the real life situation, how the real solutions pressure changes. But to match the initial part, Henry proposed that for a dilute solution, or usually we call it as a, these are all basically ideal behavior, we call it as an ideal dilute solution. The mole fraction, I mean like or the partial pressure of B in that solution will be nothing but equal to some constant times the xB, which means actually it is proportional to the mole fraction of B, but that constant is an empirically derived constant and which will be obtained from the slope of this curve. So this is the Henry's law, and then we see when actually Henry's law is valid and when the Raoult's law is valid. So it is again Henry's law is from the solute's perspective. When actually you have a very dilute solution, the solute is in less amount, but the departure is more from the ideal solute, which is in solid, I mean like pure solute if you think, and then if you think and the solute in a very dilute solution, because then the environment is very different, there are a lot of solvent molecules around, so which we depicted in this figure. So it's a very different environment, so actually the deviations will be huge. But when we are adding the the xB, or the increasing the mole fraction which is xB, we see that B is actually reaching a pure state, then actually it will behave as if actually it's just like a solvent, and then our Raoult's law will be valid. So this is the major difference between Henry's law and Raoult's law. And then you can also get some expression for Kb. Again, this Kb is a proportionality constant, it is just an empirically derived quantity. And then the next thing what we discussed in the previous course is basically known as colligative properties. Now, colligative means actually it's a collective property, and again, there are several observations like freezing point depression, melting point, boiling point elevation, and then also osmosis and solubility. All these things you can actually explain based on the change in the chemical potential of the solute in the solution. Now, what do you mean by that? Let us just draw our phase diagram for any general system, and suppose we are plotting the chemical potential and versus temperature, or the Gibbs free energy versus temperature. And we know that initially, the solid actually dominates, and this will be the mu versus T curve for the solid. And then there is a phase where actually the liquid dominates, and this is the cross point for solid and liquid. So that cross point we basically call it as a freezing point, and then finally the vapor actually dominates, and this is the vapor temperature curve, and this is the boiling point. Now, what happens here is that if we suppose this is suppose for a pure liquid, let's say water. Now, suppose if we add salt into water, what will happen? So this is for solid, this is for liquid, and this is for vapor. Now, this is for pure water again. Now, if I add some amount of salt into the liquid water, what will happen? The chemical potential due to actually a new constituent will actually decrease in solution. So the new curve will actually lie somewhere here, new curve for the liquid. So this is for liquid pure, and this is liquid in solution. Now, as a result, as we can see, the cross points of the liquid curve with the solid and the vapor has now changed. Now, why we are not changing the solid and the vapor curve? The assumption here is that when you are adding a salt, when we have the vapor phase at a very high temperature, in the vapor phase only water goes, not the salt. Similarly, when we freeze it, the water actually, the assumption here is that the water is actually freezing out from the solid. So, in the solid phase or in the vapor phase, it is always the pure water. There is nothing called a solution is getting vaporized or a solution is getting solidified. So, only the solvent gets frozen or the solvent goes into the vapor phase, but not the solid. So, this will be true for a non-volatile solute, something like a salt, and this salt will actually change the chemical potential of the solution only in the liquid phase. So, as a result, what we can see here, the new freezing point will be actually lower than the earlier freezing point, and the new boiling point will be actually higher than the earlier boiling point. And so, this is known as basically freezing point depression, because we are having a lowering on the depression in the freezing point, and then we are having elevation in the boiling point. So, this can be successfully explained from again by working out the changes in Gibbs free energy, and if you calculate it, you can actually get an estimate for the boiling point elevation, and that you can again connect it to some constant times the mole fraction of B, and that constant if I assume the ideal behavior, so we can show it that it will be nothing but RT square divided by delta H. Now, this process is basically vaporization we are talking about, because it is a boiling point elevation, and it's delta H vaporization into XB. Similarly, you can also get a similar expression for the freezing point depression, and you can show it, it will be something like RT star square. Now, T star is basically corresponds to the pure freezing point or pure boiling point according to this equation. and this delta H will be nothing but delta H fusion times XB. So these are again empirical relations that actually connects the boiling point elevation and the freezing point depression. And this up to this actually we talked about the thermodynamics of mixing, and then in some courses we actually discuss the phase diagram of multiple components, and which we actually did not discuss in the earlier course. There are also one more part is remaining, which is the thermodynamics of electrochemical cells and also chemical equilibrium. So we will first cover these two topics, which is the thermodynamics of chemical equilibrium, and what are the conditions that actually modify the equilibrium constant, and then we will move on to discussing about the thermodynamics of electrochemical cells, and from that point onward we will be talking about electrochemistry and in much more detail. And there will be a thermodynamics part of the electrochemical phenomena where we will talk about the stability of colloids and many other interesting properties, and there will be also a kinetic phenomena where we will be talking about movement of ions, and this movement of ions is connected to the electrical conductivity. So those things we will cover, but first we will give you an overview of the thermodynamics of electrochemical cells. Thank you.